Let's draw and explain the normal end-tidal CO2 trace, or capnogram. Axes, time, kilopascals, labelled from 0 to, let's say, about 5. And the shape looks like this. So it's kind of a square wave, but the top's not flat. So we start off at 0, and then over time it will rise at an increasingly rapid rate, and then it'll drift off and plateau, but still climb very slowly, and then suddenly drop again. So why is it this shape, and what do each of the phases represent? Well, we're going to divide it into 4 phases. Phase 1 is this bit here, before anything happens. This is called the dead space phase. Phase 2 is from when you start to get some CO2 coming out to here. This is kind of a mixing phase, and we'll explain each of them in a minute. Phase 3 is the alveolar plateau phase, and phase 4 is when the CO2 drops to 0, because this is the inspiratory phase. So what do each of the bits mean? So start here. The dead space phase occurs because when you breathe out, the first air to leave your respiratory system is the air that was in your mouth and your trachea and your bronchi and all the other bits of your lung that don't do gas exchange, haven't got any CO2 in them. So the gas that you're exhaling is just unchanged gas that you've inspired. So there's no CO2 in it, generally speaking. So you exhale that first, and that doesn't have any CO2 in it, so it stays at 0. And then once you get to the start of phase 2, this is when you're getting the first alveolar gas starting to come out, and that's got CO2 in it. Now, not all the alveoli are going to empty or fill up at the same rate. They each have what's called a time constant, which means how quickly they fill or empty. And different alveoli have different time constants. So there will be a period of time where you are emptying some of the first alveoli, but some of the other areas of the lung are still emptying non-gas transferring airways. So you've got a mixing of some CO2 containing gas and some dead space gas, which is why it starts to increase, but it starts off low. And then as time goes on, increasingly you've already emptied all of the non-gas transferring airways, and you're just now emptying alveoli. That's what happens when you get to the plateau phase. At this point, you are only emptying alveoli, you've got rid of all your dead space gas. The reason it is increasing as you go is because all the while that you've been exhaling, the alveoli that are taking the longest to empty still have CO2 being dumped into them by the blood. So while we've been breathing out our dead space gas and then starting to breathe out our alveolar gas and then breathing out a bit more of our alveolar gas, the last alveoli to join in have been filling up with even more CO2. That's why they have more CO2 in them, and as a result, the measured reading is higher. So the end of the trace is always higher than the start because of this process. And then when the patient takes a deep breath in again, they draw fresh gas past the sampling tube, and this drops to 0 as the gas doesn't have any CO2 in it, and so none is measured. The final thing to mention is the alpha angle. The alpha angle is the angle between phase 2 and phase 3, and it's supposed to tell us about the VQ, or ventilation perfusion matching. So we talked before about the lungs have to coordinate sending the gas to the areas of the lung where the blood is also being sent. You have to match the ventilation and the perfusion, and this angle here can give us an idea of how well that's working. So in general, in healthy lungs, if you've got a good ventilation perfusion matching, this angle will be about 100 to 110 degrees. If you've got COPD or asthma, you've got more lung units that are going to take longer to empty. So as a result, this becomes steeper, and so that alpha angle becomes much bigger. We're talking more than 110 degrees. It'll look more like this. And so the end tidal CO2 is the end of the breath out, which is this point here, and it'll be your maximum point, your highest CO2 reading. And a normal value is anywhere sort of 0.5 kilopascals to 5.5 kilopascals is what we would consider normal. And you might get asked, why might you have an increased end tidal CO2? Well, if your CO2 is high, you're either producing more CO2 or you're not getting rid of it quickly enough. If you're in a hypermetabolic state, so you're producing a lot more CO2, such as fever, sepsis, or malignant hypothermia, or if you're not ventilating effectively, which is more common, so you're just not breathing quickly enough, and so the CO2 is building up. In an anaesthetized patient, this might mean you just need to ventilate them a little bit harder. And your end tidal CO2 might be low because your CO2 production is low, or you're ventilating them too much, or there might be a disconnection in your breathing circuit, Or it might be a cardiovascular problem and they're not delivering the CO2 from the cells to the lungs. So if someone has got a large pulmonary embolus, or if they have got a very low cardiac output, then their end-tidal CO2 will drop dramatically because they are making the CO2 in their cells, but they are not delivering it to the lungs. And added to disconnection, we can also say sampling error. That's one of the key things in anesthetics, is you're using machines a lot. So it could always be a patient problem or a machine problem. That's a brief overview of the normal end-tidal CO2 trace and why it's the shape that it is. And we have other videos talking about the pathological states when this is not normal.